Nuclear radius. The results from Rutherford's alpha scattering experiment allow us to find the ratio of nuclear radius to atomic radius. He found that about 1 in 8,000 alpha particles were deflected by more than 90 degrees, meaning that the nuclei made up 1/8,000th of the area of the atom. If r is the radius of the nucleus and big R the radius of the atom, and the gold foil is n atoms thick, then the area of the nucleus divided by the area of the atom will be pi r squared, the area of the nucleus, against pi big R squared, the area of the atom. And this is equal to 1/8,000 times the number of atoms in the thickness of the gold foil. So we get that r squared, the radius of the nucleus squared, is equal to the radius of the atom squared over 8,000 n. N will be around 10,000 atoms. So we get that the radius of the nucleus is equal to the radius of the atom over the square root of 80 million, giving r is equal to the radius of the atom over 9,000. So the radius of the nucleus is about 9,000 times smaller than the radius of the atom. If we know the initial kinetic energy of the alpha particles, we can find an upper limit for the size of the nucleus from the distance of closest approach in a head-on collision between the nucleus and the alpha particle. The initial kinetic energy of the alpha particle will be equal to its electrical potential energy when it is momentarily stationary at the point of closest approach during a head-on collision between an alpha and a nucleus. For a 5 mega-electron-volt alpha particle, we can say that 5 times 10 to the 6 for the mega part, multiplied by the charge on the electron, 1.6 times 10 to the minus 19, this gives the energy of the alpha particle in joules, will be equal to the electrical potential energy, the charge on the alpha times the charge of the nucleus, over 4 pi epsilon naught times their separation d. Now the charge of the alpha particle is 2 times the charge on the electron, as it contains 2 protons. The charge on the nucleus in this case is 79 times the charge on the electron, as the nucleus is gold with 79 protons. So we can rearrange the equation and put in all the values given, and this gives a distance of closest approach, and therefore an upper limit to the size of the nucleus, of 4.5 times 10 to the minus 14 meters. Another more accurate way of finding the radius of the nucleus is by the diffraction of high-energy electron beams. Just as light gets diffracted as it passes through a gap, if the gap is a similar size to the wavelength of the light, electrons are diffracted as they pass through a gap of a similar size to their de Broglie wavelength, where the de Broglie wavelength is given by hc over E, where h is the Planck constant, c the speed of light in a vacuum, and E the energy of the electron. The electrons are diffracted by the nuclei when their de Broglie wavelength is similar in size to the nuclei. On top of this diffraction effect, the electrons are scattered by their attraction towards the positive nucleus. When the results are analysed, nuclear diameters are found to be around 10 to the minus 15 meters. To find out how the nuclear radius depends on the nucleon number, we can measure the nuclear radius of several elements. Then, if we plot a graph of the natural log of nuclear radius against the natural log of nucleon number, we get something like this, where the gradient comes out as a third, and the intercept will be the natural log of r0, the radius of one nucleon. This gives the relationship that the natural log of r is equal to a third the natural log of a, plus the natural log of r0, the nucleon radius. This equation is of the form y is equal to mx plus c. Removing the logs, we get this expression, that the nuclear radius r is equal to the nucleon radius r0 times the nucleon number a to the third. So if we plot a graph of nuclear radius against a to the third, nucleon number to the third, we should get a straight line through the origin. This line has a gradient equal to the nucleon radius r0.